Justin Miller, Arts College Physics here. What do we got? We got some more projectile motion problems to look at. So here's another problem that we're going to take. This time we're going to actually throw something kind of upward and discuss some aspects of its motion. So here's the problem. All right, so we've got an object that is thrown or projected at an angle of 65 degrees relative to the horizontal with an initial speed of 20 meters per second. Then we're asked a bunch of stuff like, hey, how high up does it go? How long is it in the air for? How long does it take to reach its max height? How long is it in the air for? What's its total distance in the, its total displacement in the x direction? What's its velocity as it reaches the ground? So let's again draw out a nice little picture regarding this. So we're taking an object that is initially at ground level and it's going to return to ground level. So that's a nice case. So just take this, there's ground level right here, and we're going to take that object to have some initial velocity that is 20 meters per second at an angle of 65 degrees. So there's 45, 65, we'll say is something about like that. We've got ourselves v hat initial is equal to 20 meters per second at 65 degrees. So that's a 65 degree angle relative to the horizontal. What's this object gonna do? It's gonna fly through the air, right? So we can kind of draw out what we might expect it to do. It's gonna do something like this, right? Something like that. So let's just kind of draw that out. Goes up, comes down. That's kind of messy there. Shameful mess. It's okay. I take it. So there we go. Goes up, comes back down. You know what? I'm just not satisfied with that. Sorry. So we've got this. That looks much more satisfying to me, maybe not to you, but that'll come into play a little bit later on. So there's its trajectory. Eventually, yeah, it's going to reach the ground over here. And we'll have some velocity vector that looks kind of like this. V final hat, we'll have some angle, theta V final, and that's it. So, what do we have here? Well, the first thing that we're asked is, what is its maximum height relative to ground level, or really what's the maximum displacement in the y direction? So we've got this. When it reaches its maximum height, that will define delta y max, right? So what do we know about this? Well, A, we want to know what delta y max is. What do we need to have in our bank, in a sense? Well, talking about the y direction here, we have some Vy initial, we have some Vy final, and we've got some time. So those are the quantities regarding the y direction. And really, we want to be able to figure out what is this, right? So the question becomes, well, which of these three quantities do we know? We better know two of them to be able to solve for this one. So, where's a good place to start? Best place to start is take this initial velocity and resolve it into its x and y components. So, first, get Vx initial and Vy initial. That's always going to be a good place to start. Find the components of the initial velocity. So Vx initial is equal to the magnitude, we'll just write it down, the magnitude of V initial times the cosine of a theta V initial, which is going to be equal to 20 meters per second times the cosine of a 65 degrees. And Vy initial is the magnitude of V initial times the sine of a theta V initial, which is 20 meters per second times the sine of a 65 degrees. So we'll just get both of them because we're likely going to need them, even though we only need Vy initial for this particular part. We just do them both. So we've got 20 cosine 65 and 20 sine 65. We've got ourselves 8.4524, we'll call it. 8.4524 meters per second for the initial x component, and 18.126 meters per second for the initial y component. So there we go. We've got these components there, Vxi and Vyi, and now we know this, right? Vy initial is 18.1262. 18.1262 meters per second. Notice that even though we threw this at 20 degrees, most of the initial velocity is in the y direction. Why? That has to do with the angle. If we would have thrown it 90 degrees, that's all straight up. We'd have the y component's 20. As we reduce that more and more, well, the x component gets larger and larger. And well, at 45 degrees, we'd have even components. And then as we go below 45 degrees, the x component gets greater than the y component. Until, well, theta 0, and then we'd have, just like we had in the other problem, the initial velocity in the x direction would be the initial velocity, 20 meters per second. But nonetheless, 65 degrees, this is what we get. So we want delta y max. Do we know how long it takes to get to its maximum height? Are we told that? We can figure it out, but it's contingent upon knowing something else. And that is specifically, what is its velocity when it's at its maximum height? Vy is equal to 0 at delta y max. When it's at its maximum displacement in the y direction, the velocity in the y direction is 0. Again, it stops going up, starts coming down. That's the transition spot. So we know what this is. Even though it's not specifically stated in the problem, it's something that is extracted by the question that we're answering. What is its displacement, what is its maximum displacement in the y direction? So this occurs at delta y x. So now we know two pieces of information. We can go ahead and figure out what this is. So how are we going to do that? We go ahead and look at our equations that we've got going on. So let's write those down again. You've got something like delta y is equal to negative 1/2 g t squared plus vyi times t. Vy final is equal to negative g t plus vy initial. Vy final squared is equal to Vy initial squared minus 2g delta y. And what we want to know is which one's going to help us solve things. Well, it all depends on what we know and what we don't, right? We do not know time. So neither of these is going to be helpful because they both involve time, which we don't know yet. Which leaves us with this one. So we look at this particular, this particular expression and say, can we solve? Well, yeah, we know Vy initial, we know Vy final. Delta y is what we want to know. So let's just use this one. So we've got ourselves, from this, 0 for Vy final is equal to Vy initial squared minus 2g, and this becomes delta y max because delta y max correlates with Vy final there. And then we can just solve this for Vy final, for delta y max. Delta y max is going to be equal to, subtract this from both sides, divide by negative 2g, negative signs cancel out, and we've got Vy initial squared divided by 2g. So now it's just a matter of evaluating it, right? We've got that Vy initial is 18.1262. So 18.1262 meters per second, quantity squared, divided by the quantity of 2g. Be really careful putting this in your calculator. Generally, this needs to be in parentheses. If you don't put this in parentheses, unless you've got the math writer itself activated, it will take this number, divide it by 2, if you put 2 first, and then multiply it by g. So make sure you group this in parentheses in your calculator. Otherwise, you may have it written out right, but you get the wrong answer. All right, so let's do this. We've got 18.1262 squared divided by the quantity of 2 times 9.8. And I get 16.763. 16.763 meters. there is its maximum displacement in the y direction. Throw the object at 20 meters per second at an angle of 65 degrees. That's how high up it goes from its initial location. That's it. Doesn't matter what the object is. If that's what we give it in terms of its initial state, that's part of the outcome, or part of the evolutionary behavior of it. All right, so we've got its maximum displacement. Great, we know how high up it goes. What happens if we want to know, hey, how long does it take to get to that maximum height? Let's get T up. Time to reach delta Y max. We're still kind of in these realms right here, right? We got Vy initial is 18.1262 meters per second. Vy final at the maximum height is still equal to 0. So now it comes into, hey, we want to know what T is. So how are we going to get T? Again, we look to the equations that we have here. And this one's going to be the easiest way to go about it. We know what Vy final is. We know what Vy initial is. We can go ahead and solve this for T and get ourselves that Vy final is equal to negative T plus Vy initial. And then we can solve that for T. I'm just going to move some stuff around. And we've got that T is then equal to Vy final minus Vy initial divided by negative G. Vy final minus Vy initial divided by negative G. And then we can go ahead and put in what we know about this. Well, we know that Vy final is equal to 0. So that's going to leave us with negative Vy initial divided by negative G. The negative signs are going to cancel each other out. And we're going to get that this is going to be equal to Vy initial divided by G. What is that? Well, that is going to be equal to 18.1262. 18.1262 meters per second divided by G, which is the 9.8 meters per second squared, leaving us with some seconds. 18.1262 divided by 9.8 gives us 1.8496. T up is equal to 1.8496 seconds. So that's how long it's going to take to reach its maximum height, based upon, again, its initial velocity being 20 meters per second at an angle of 65 degrees with respect to the horizontal. Great. Let's ask, hey, how long is this object actually in the air for, from when it starts to when it reaches the ground? What's the total time it's in the air for? Let's see if we can make some correlations here. Let's see. T total. Total time in the air. Well, if we want to figure that out, we've got ourselves some new things going on. We've got a delta Y to consider, a Vy initial, a Vy final, and a T. We're asked for that T right there. We know that Vy initial is 18.1262 meters per second. We need one more piece of information to be able to figure out time, right? So we ask ourselves, what do we know? Do we know what the final velocity of the object is? Well, we know what it is when it's at its maximum height, but we don't explicitly have what it is when it returns back to the ground. So this is an unknown at this point. So we better know what delta Y is, right? Well, think about this. The object starts at this level, goes up, comes back down to the same level. What's the difference in the elevation between where it started and where it ended? Y initial, Y final, same elevation. So Y final minus Y initial is going to be equal to 0. Its total displacement in the Y direction is 0. Returns to initial elevation. So we know those two pieces of information. We want to know what T is. How are we going to go about this? Well, let's look at this. We go back to our equations up here. We want to figure out a T knowing what delta Y is. There's no T in here. There's no delta Y in this one. There's a delta Y, there's a T, and there's a Vy initial. So we should be able to use this expression here to figure out what T is. So let us go ahead and write that one down. We've got ourselves that this part C. Oh, I've already drawn it there. That's okay. We've got ourselves that delta y is equal to negative 1/2 g t squared plus vyi times t. So here's the thing. This term is non-zero. This term is non-zero because Vy initial is not zero. It's 18.1262 meters per second. So does that mean we're going to have to use a quadratic formula? Nope, it doesn't. Because this term is zero. Delta y is zero. So what do? Yeah, we stick that in there. Zero is equal to negative 1/2 g t squared plus Vy initial times t. So there is what we want to solve. There is a specific t or t's that will explicitly solve this expression here. So let's try to figure out what that is. I'm going to factor out one t because we've got a common term. Each of them have at least one t term. So I can write this as 0 is equal to t times negative 1/2 gt plus Vy initial. So the solutions really are that 0 is equal to t, or 0 is equal to negative 1/2 gt plus Vy initial. If t is equal to 0, 0 times this is equal to 0. If this quantity here is equal to 0, 0 times whatever t is equal to 0. So this one, t equals 0, is where the object initially is, right? So yeah, its displacement is 0 at t equals 0 because it hasn't moved. We're looking for the later time at which it returns to its elevation. So that's going to be gotten by this expression right here. So we go ahead and solve that for t. I can go ahead and subtract Vy initial from both sides, multiply by negative 2, and divide by g, and isolate t there. So we go ahead and do that, and we can get ourselves that t is equal to negative 2 times negative Vy initial divided by g. So this is negative for moving it over. There's a negative there, there, there. The negative signs cancel each other out, right? And we get 2 Vy initial divided by g is the total time that it's in the air. So we can go ahead and put a t total there. Well, what I want to do before I actually quantify this is compare this to the time it took to reach its maximum height. This right here, Vy initial divided by g, was the time that it took to go up to its maximum height. This is the total time that it's in the air. 2 times Vy initial divided by g. 2 times this quantity right there. What does that tell us? It tells us that the time it took to go up is the same amount of time that it takes to come back down. Because the total time that it's in the air is 2 times the time it takes to go up. So that's just like what we had with just plain old one-dimensional free fall. We've got equal amounts of time for equal displacements that take place. Time up equals time back down to the same elevation ultimately. So that is something that we could just say, hey, it's 2 times this. Only though because it's coming back to the same elevation from which it began. Delta y is equal to 0. Delta y is not 0, that's not the case anymore. Anyways, we compute it out. T total is equal to 2 times 18.1262 meters per second divided by g, which is divided by 9.8, gives us 3.6992. 3.6992 seconds. There's the total time it's in the air, which is twice the amount of time that it took to reach its maximum height. Great. Love it. All right, let's ask one more thing here. Let's ask ourselves, what is the maximum? No, let's not ask one more thing. Let's ask a couple of things. What's the maximum displacement in the x direction? How far does this object move in the x direction? What's its range? When it comes back down to the same elevation from which it began, how far has it moved in the x direction? I'm going to erase that right there and say that we want d delta x max. The range. Well, that is this right here. Delta x max. Starts here, moves over to there. So how are we going to get delta x max? Only got one expression that gives us anything with respect to the x direction, right? One real expression. We've got ourselves delta x is equal to vxi times t. So if we know what the initial velocity is in the x direction, and we know the time interval that we're considering, we know how far it's moved in the x direction. We want delta x max. Delta x max is going to be equal to vx initial times t total. That's it. Do we know what t total is? Yes, we do. 3.6992 seconds. Do we know what vx initial is? Yes, we do. It's 8.4524 meters per second. That was one of the first things that we figured out. What is the x component of the object's initial velocity? So with that, we've got that delta x is going to be equal to 8.4524 meters per second multiplied by 3.6992 seconds, which gives us, this is max, delta x max is equal to, I grab this one, that times 8.4524, which gives us 31.268. 31.268 meters. You take an object, you throw it at 20 meters per second, the angle is 65 degrees, and by the time it reaches the ground, it will have traveled 31.268 meters, which is pretty far. That's almost 100 feet or so. Or about 100 feet. Anyways, that's it. That's it. So one last question. That's going to be, what is this? What is this final velocity? How fast is the object moving, and what direction is it moving in as it reaches the ground? Ourselves a party. Party. All right, part E. V final is equal to what? You want a magnitude and a direction. So let's go ahead and figure out what that is, right? Well, this is what we've got. We've got V final hat is going to be equal to Vx final I hat plus Vy final J hat. All right, that sounds good, right? So what do we know about this? Do we know what Vy final is and Vx final is? We do know Vx final because there is no acceleration in the x direction. That is to say, Vx final is equal to Vx initial is equal to 8.4524? 8.4524 meters per second. This. There we go. What we need is what is the final velocity in the y direction when it's reaching the ground. So we need this. How are we going to get it? We know Vy final is equal to negative gt plus Vy initial. And we know that t total is our 3.6992 seconds. T is equal to 3.6992 seconds. And Vy initial was our 18.1262 meters per second. So we can figure out what Vy final is. Well, that's one way to get it. I want to look at this a different way. We could easily compute this. Easily, let's just compute it really quick. Let's solve this for Vy final. Vy final is equal to negative g times 3.6992 seconds plus 18.1262 meters per second. Gives us a Vy final is equal to, go ahead and stick that in our calculator here and give ourselves 9.8 and negative 3.6992 plus 18.1262 gives me 18.126. There's a little significant figure stuff going on, 1262, but we got some random values, so I'm just going to call this, so it's negative 18.126. Negative 18.126. Actually, if we expanded this out to all significant figures in this one as well, this would actually be negative 18.1262 meters per second. Uh-oh, excuse me. Sorry about that. Meant to have my ringer off. Anyways, here we go. What do you notice about that? Well, its initial velocity in the y direction was positive 18.1262 meters per second. It goes up, it comes back down the same distance that it went up, returns to ground level with the same speed in the y direction that it initially had. It's just going downward now. Again, just like with free fall, there is symmetry in its velocity in terms of going up and coming back down over equal time intervals, over equal displacements. So this is something that's there. That's it. So we've got Vy initial. Now I was saying, let's look at this a different way. Excuse me, Vy final. Saying, let's look at this a different way, and that is simply looking at this third expression here. We've got Vy final squared is equal to Vy initial squared minus 2g delta y. Delta y is equal to 0 upon returning to its initial elevation. If delta y is equal to 0, that term goes away, and we've got that Vy final squared is equal to Vy initial squared, which gives us that Vy final is equal to plus or minus the square root of Vy initial squared. Take the square root of both sides, and we'll ultimately get Vy initial. Well, it was initially going up, now it's going down. So this plus or minus really resolves into Vy final is equal to negative Vy initial. Same speed going up initially that it is going down finally. There's our negative sign right there. So either way, we figure out that there's symmetry within the going up and coming down aspects. Equal time intervals over equal displacements result in equal changes in velocity up to down. So let's go ahead and finish this up, figure out what is this final velocity as a magnitude and direction. So what do we have? We've got ourselves final velocity overall. We've got ourselves V final hat is equal to, well, its magnitude is equal to Vx final squared plus Vy final quantity squared, which is then equal to the square root of 8.4524 meters per second quantity squared plus a negative 18.1262 meters per second quantity squared. Go ahead and throw that in our calculator, and what are we going to get? Go ahead and do it, and you find that calculator gives you 19.99999. What is that? Well, that's 20.0 meters per second. The same overall speed that it initially had when it was projected. Calculated out, it's the same thing. So goes up, comes down with the same velocity because it's returning to the same elevation. We go ahead and compute what the angle is, and we note that that is the arctangent of Vy final divided by Vx final, which is then equal to the arctangent of negative 18.1262 divided by 8.4524. And what's that going to be equal to? Put it in your calculator, calculate it out, and you're going to get yourselves negative 65.0 degrees. Same initial angle up that the final angle is pitched downward. There's symmetry about the positive x direction. So in the end, we've got ourselves that V final is equal to 20 meters per second at an angle of negative 65 degrees. That is, again, because it comes back down to the same elevation from which it began. Same final speed as initial, and symmetry about the angle relative to the positive x direction. Good problem. We'll do some more. There's lots going on with projectiles, and that's pretty much that. Have a good one.